All right, so the first question I have is from Lev. Lev, feel free to unmute yourself and go ahead.
Sean, one thing which I am fully with you, that you say that Everett is great. And that if Everett would be true, this will be best solution. I may add, of course, deterministic, simple, elegant, maybe more local than others. I also thank you for promoting self-location and uncertainty, although you know that I feel that your presentation doesn't work. In your slide, when you said about this probability, when we have a probability uncertainty, self-location uncertainty, you had observer in one quantum state. It was multiplied by measuring devices which were in different states and also environment. And you emphasized the coherence, which I don't think really is needed. I think Everett was fine. We don't need environment because you put your devices macroscopic, so they already separated the worlds. So you had two worlds in your measuring device, one outcome, another one, but you had only one observer. There cannot be meaning to ask in where he is located. There is only one location for observer. He doesn't have any uncertainty about self-location in this case. It seems that you felt that there is some difficulty here, or maybe because I was trying to tell you many times that this doesn't work. And you said that let's ask another question, where he will end up in the future measurement. I think this is worse. The whole, for me, is the main question which you cannot ask in Everett. What is the probability that you will end up with particular outcome? Because you get all outcomes. Therefore, there is no probability for future outcomes. Does not exist. It does not mean that you will not behave as if, but there is no probability because all outcomes are happening there. Then came Dave and brought the Kirk scenario. And if you make quantum Kirk scenario, then I think this is a clean experiment. We have two Kirks, one in green and one in red. So there are really different Kirks, and you can ask the question, self-location question. Am I in green Kirk or am I red Kirk? Then they started to say that there are some small worries that maybe it's too late and it's not answering the question, what will be the result of future measurement? And I think Dave is absolutely right. There is no such thing like probability for future measurement. It doesn't supposed to solve this. It's supposed to solve only this. There is this special situation, which may be not so special when as you presented, that Kirk makes this experiment. Now he's in two different positions and he doesn't know which one he is. And he thinks for him, what is my probability for being Z1 and Z1? This exists in many worlds. There is no question about what will happen in the future, because in the future everything will happen, and there is no probability for a future. But it doesn't mean that the person should not behave as if. He should care about his descendants. His descendants might have this kind of probability, and he will place a bet for them, and maybe he will care for them in all these ways. But then Dave came with kind of a serious question that I cannot really. There is no any kind of empirical way to see these quantum probabilities, which I want self-location probability, which we want to talk about. There is, I think he is right that we cannot have a priori. Indifference is not good enough. Although there are kind of some scenario you can play with some symmetric situation and then apply to symmetry, and then just indifference. If I don't know anything, I have no idea what to bet. But if somebody will tell me that all the situations are identical, then I have reason what to bet. So I'll go with Sean. When we have all amplitudes are equal, but I need more than amplitudes equal. I need them really equivalent. They all have symmetry. All these options have symmetry. Then we can have kind of indifference, and then we can try to put some a priori idea about probability. But again, it's not strong. We cannot really. We have to assume something to get a Born rule if you want to derive it. We cannot derive it from the laws of quantum mechanics. We need some assumptions, but we can make empirically confirm this. You went in lengths proving something which is absolutely correct. External entity cannot test this quantum self-location probability. If I have Wigner who can make experimental Wigner friends, super technology who will look on all of them, look all these branches, he cannot know what is the right strategy, A, B, and C. This is self-location. Only the person himself can know this. You kind of accept it, but you completely dismiss it. Just to be sure what is the scenario. The Kirk repeats this experiment with green and blue, and let's say with quantum probability 0.9, 0.1. He goes to Earth, he records what he got, and he goes again many times. After many experiments, he just asks himself what he wants to expect as a probability. And so he will, he has to expect his probability. This is what tell us the Born rule. Now, I think he himself, just every person, there is one incident of this Kirk, and we do have many experiments like this, because I believe that there are many physics journals, and in physics journals there are papers and many experiments, and every time there is experiment, the paper is published, and I believe that there are some kind of decoherence, and my body is slightly moved depending on outcomes and what is written in papers which I didn't open them, but I know that they happen. So I open a physics journal, I see that the quantum experiment has been performed. I'm in a situation of Kirk, because I still don't know, I know what's the setup, I don't know what's the outcome. I expect, and I have empirical evidence that the Born rule is correct. So I do have empirical evidence for self-location uncertainty. This is the only way to accept it. Again, this is as if, this may be slightly strange, like in the end of the day, if one maybe special case probability works like Born rule, then it's easy to extrapolate those, so we have to do it for all. We also needed to explain physics. To explain that the sky is blue, we need Born rule. So this all kind of, this me see sky, blue sky a few hours ago. So for me, it's kind of empirical evidence that the Born rule is correct. Thanks.
I don't know who to, Sean, do you want to?
I think I'll let you go because, you know, internecine Everettian disagreements have a flavor of the Judean People's Front versus the People's Front of Judea that I don't want to bother too much with. So why don't you give it a shot?
So,
you get points for the life of Brian.
There was a lot going on there, Lev. But I take it towards the end, you were referring to this attempt that I was entertaining towards the very end of my talk, where you say, yes, there's confirmation, so on and so forth, but the confirmation is purely indexical. It's not objective, okay? What we say about these theories is that this sequence of experiments confirmed the Born rule for me. It confirmed the negation of the Born rule for other branches, for other observers. One does not try to objectively adjudicate between these different branches, okay? One merely says it's confirmed for some branches, it's disconfirmed for other branches. Questions like, is it confirmed or disconfirmed simpliciter don't make any sense, okay? So.
May just a second. Yeah. The rule is the probability of self-location is proportional to alpha squared. This is what I have to confirm.
Yeah.
I look out, I see it, so I confirm it.
No. Some people see it, some people don't see it. Some people confirm it, some people disconfirm it.
I don't know such people.
That's true.
So I know that they exist, and that there is a small measure of small chance in the universe they exist.
Wait, excuse me. No. You used words chance and probability. Their chance and probability are all one.
Oh, yeah.
So let's not muddy the waters that way. Okay. So it sounds like you're adopting a radically perspectival idea of the whole scientific project here. Theories, rules like the Born rule are not confirmed or disconfirmed. They're confirmed for me, disconfirmed for you, okay? Claims like the Born rule are not true or false of the world, okay? They're true or they may be true for me. They're going to be false for you. These other levs that exist. Okay, good. This strikes me as a quite metaphysically and sort of epistemically radical way to talk. I think there are a lot of questions about whether it's coherent and intelligible. Okay, but put those questions aside for the moment. It seems like a huge price to pay when we had, like I said, when we have these other theories that don't require anything of the sort.
If you have a fair coin and you make it, it's a fair coin. You throw it 1,000,000 times and you see its tails 1,000,000 times. Will you say something wrong here? You say it's improbable. So it's still fair coin, also for the person who's finds it strange. The same. So this is true for all of me. This of me, just see, happens.
Lev, there was a long section of my talk devoted to exactly this example, devoted to showing the disanalogy, okay, between the example you just gave and the self-locating probability example. Now, maybe you think there was something wrong with that section, and I'm anxious to hear it, but you can't just assert that it's the same. I spent 15 minutes arguing that it wasn't the same at all.
Okay, I don't want, there are some maybe more people, and maybe Sean wants to say something.
Yeah, sure.
I mean, I'm looking at how time is flowing here. I would rather just get more questions in.
All right, thanks. Thanks, Lev. Next question is from Carlo.
Okay, let me unmute myself. Hi. First of all, thanks for this. This is a question for Sean, because I think my disagreement is larger with Sean than with David on this. First of all, the question is short. Let me make a short general comment and then a very specific question. The general comment is that I think that the problem about each of the interpretation of quantum mechanics is that the one which are most discussed, they're all good. And this came out in the discussion between Sean and David. When Sean said, can you prove it wrong? And David said, no, but that's not the point. The most interpretation which are on the table cannot be proven wrong or cannot be proven insufficient or bad. The point, and this again came out in the discussion, is that each of them come with a price. And somehow we all focus on the cost and the price of the interpretation which we know less, and we discard because they seem that price to be very, very high. Sean says, oh yeah, Bohmian has a price that for a physicist is too high. You know, break Lorentz invariance, break this, break that, or whatever. It doesn't seem useful. And David says, yeah, but this sort of mad dog Everettism comes with a price. So this is Baroque philosophical demand on our imagination. I think, in a sense, all these discussions are a bit of losing time, because of course each one of them has a very high cost. Otherwise we would have converged on one that doesn't have any cost. The problem is comparing the different prices, the different conceptual prices, different sort of philosophical costs that they demand us, and whether they push us. In this sense, Sean's talk was nice because it said where it's pushing us, this sort of mad dog Everettian interpretation. The weakness seemed to me that Sean, you seem to present it as too much of an open, it's not a closed interpretation. It's not, look, quantum mechanics as it is, a non-relativistic quantum mechanics, I can interpret this way and it makes sense. It had to hang, in a sense, on the spectrum of the Hamiltonian, knowing anything about the system, which were very much open-ended situations. Now, let me come to the question, because that's where I want to go. And I, as you know, I come from a different perspective. I feel more comfortable with a relational interpretation, which is it's also Everettian, but it's 100% away from you, in a sense. It's forget the wave function. The wave function is just a later construct. What we're talking about is facts, real facts that happen, and the real probability that connect the occurrence of these facts at different times. I hope that Jacob at some point will give me the opportunity for talking about the relational interpretation. But I mentioned that because so my question makes sense. You said, Sean, that everything is in your first slide, which was basically Hilbert space and vector and Schrödinger equation. And then you gave the intuition in your branching slide, in which you have this wave function that branches, and the entire story is about branching. Now I find something very clashing between the first slide and the second slide, because the first slide is time reversal invariant. And very clearly so. There's absolutely nothing that breaks time reversal invariance in the fundamental equation that you showed in the first slide. But then the story, the interpretation is all about branching, and branches toward the future, but not toward the past. Now we do understand, of course, difference between future and past in a time reversal invariance environment, which is in terms of entropy and low past entropy. And David is teaching us a lot about that. We can use his language. We assume a past hypothesis. This, at the very least, seems to be missing in your presentation, besides what you said, the missing structure, the missing observable that have to be derived. But there's something else. You're assuming something heavy about the past. In other words, the simple question is, why don't things branch to the future, and why do they branch to the past? Why they branch to the future? It's different from the entropy case, because the entropy, we can actually measure it. We have a cosmology with an account of how higher was the entropy in the past, and we can measure the entropy at some point and some other point. It's different. We see it going up. While when we make measurement, the entropy is not going up. It's all. And last comment about that, and it's perhaps the key of the story, there is a beautiful paper that I think everybody should know and is not known enough by Einstein, together with Tolman and Podolsky, in which he makes a marvelous point, which is that if we know something about the present, we make a measurement, or there's some fact, or some information about the state, if you want, of the universe today, we can make probabilistic statement about the future, and we can only make probabilistic assessment about the past. So quantum mechanics, textbook quantum mechanics, if you take it seriously, is telling you that given the present, the state branches toward the past equally as toward the future. But then your entire intuition about branching universe, I don't understand it anymore. So why is that branching to the future, not to the past?
Yeah, I think, I mean, maybe this requires a longer sit down over coffee or some more stimulating beverage, but in my mind, it is exactly the same as the statistical mechanical case. You need a past hypothesis. In fact, it's probably the same past hypothesis since the world ultimately is quantum mechanical. You're right on the face of it that if all you have was the first slide that I showed you, branching would be toward the past just as much toward the future. I think that the logic there is precisely analogous to Low-Schmidt's reversibility objection to Boltzmann's statistical mechanics, and the resolution is the same in both cases. That there is an initial condition. There's a past boundary condition. I did not read Einstein's paper. Sorry about. I believe it is beautiful, but I probably was not in the context of Everettian quantum mechanics. And I think that that is absolutely. I would love to somehow, so part of what this is probably just too speculative to even say out loud, but part of what I tried to get at in the latter part of the talk was the prospects of addressing certain puzzles in physics dynamically in the Everett interpretation, which simply have to be posited or taken as additional laws in other versions of fundamental physical theory. The past hypothesis might be one of those, right? I mean, we might at least aspire to be able to understand why the dynamics of the wave function in Hilbert space generically lead observers to see something like a low entropy past. I can't actually argue that that's true in the real world, but that's the kind of thing we can try to do in Everettian quantum mechanics that might be hard elsewhere.
But how you know that there weren't branching parts in the past? Or another question, let me just reformulate the question. In statistical mechanics, the past hypothesis can be formulated at least in one way very clearly. We have macroscopical observables, and we say that the entropy of those was low. So the macro state is such that there are few microstates corresponding, say, for instance. So what is the corresponding form of the past hypothesis that would produce branching toward the future? And how do you know that there isn't, in other words, if I take Everett, I'm also an Everettian, but what Everett tells me, if I read Everett, what I read in Everett is that the state I'm talking about is always a relative state. While if I read you, is that the state I'm talking about is just something else than the relative state, is a universal state. So in my reading, you're the less Everettian person I know. Of course, if you have your state, I can read out in it the Everett relative states, but not the other way around. And so if I have the relative state, I of course know that why the system is disentangled from the rest, just by assumption to starting with, not because it is disentangled from the rest. Well, you seem to me you're making a big metaphysical assumption about the state of everything, that in the past everything was disentangled and somehow get entangled with time and therefore branches. Where does it come from?
Yeah, so keep in mind, as we all know, Everett's published paper was called The Relative State Formulation of Quantum Mechanics. After a long, very torturous dialogue with his extremely Copenhagen sympathetic thesis advisor, John Wheeler, his actual title that he handed in originally was The Theory of the Universal Wave Function. That's how Everett thought. So I am actually being very Everettian in the way that Everett wanted to be. Of course, you have both. You have both the universal wave function and the branch that you're on. That's the relative state, and I think it's completely compatible. The reason why I know that there weren't more branches in the past that congealed into my present state that I observe is the same reason that I know, in some broad sense of the word know, that I'm not a Boltzmann brain that has fluctuated into existence very recently via traditional statistical mechanical fluctuations. Namely that, as David said in a different context, that's no way to go through life. Like I can't actually, that's a skeptical scenario which doesn't let me draw inferences about the past. So I posit as an assumption that there was a very unentangled state in the past. There was a past hypothesis of low entropy and low entanglement, low branch number, And from that, I can, self-consistently test that it matches my experience and lets me do science. So that's what I choose to do.
All right, in the interest of time, thanks so much, Carlo and Sean. I'm going to move on to our next question. It looks like Isaac Wilhelm is here, and Isaac, you came up in David's talk, so I think it's only fair to give you the next question.
Thanks, thanks, Sean and David. So I wanted to ask David, I wanted to ask you a few more questions about the stuff you were saying right at the end, which I might not have caught. So I understood you, I might not have caught it correctly. I understood you as saying that you thought something about this more centered proposition approach would diminish what science was doing. I think I misunderstood.
I mean, by definition, maybe this is something one can argue about whether one finds it important. Diminish the objectivity just in the sense that locutions like I've confirmed this theory, I've disconfirmed that theory, or this theory is true, that theory is false, now require an index. Okay.
So, yeah, I wanted to disagree with that. So here's why. I'm thinking of these more centered approaches as strict expansions of the range of phenomena that the Everett interpretation accounts for. It accounts for all the same de dicto phenomena and de re phenomena that was already accounted for. It's just now also accounting for de se phenomena, and it's solving the probability problem by moving the target of the analysis from being inside the de dicto to being inside the de se. That's what you're doing when you make these claims
but I don't
about
understand,
centered
Isaac.
chances.
There were other interpretations of quantum mechanics, like Bohm or GRW or something like that, don't account for these probabilities as they say at all.
They account for certain assignments of probability.
It's not like they don't discuss these probabilities. They do discuss these probabilities, but they don't discuss them. They don't discuss them as indexical phenomena. They discuss them as non-centered.
Yeah, no, I agree with that. Distinguish two types of probabilities you could want your physical theory to account for. Probabilities that don't are not assigned to propositions that are expressed using indexicals. Call those uncentered propositions. Those are propositions like David is on this branch, or like the thus and so is going to come out such and such. That's one class of propositions you can assign probabilities to. And then there's just this other class, the de se centered propositions, which are properly expressed using indexicals. Here's one reasonable reading of what Bohm is doing. They're giving an account of probabilities for that first class of propositions.
Right.
And not at all. They're not talking about any probabilities for that are being assigned or could be assigned, maybe by a best system or something, to the centered propositions in the other class. And what I'm thinking is going on in Everett, or one reasonable way of understanding probability in Everett, is thinking that it's just it's talking about assignments of probabilities to different objects, different propositions, these centered propositions. But it's not giving up on a story of those uncentered propositions. It's going to give accounts for those uncentered propositions in terms of Schrodinger evolution of the wave function, grounding stories for how you get macro phenomena out of micro phenomena, and so on. That's why I think it's a strict expansion of the account of the phenomena to be discussed.
But that seems a little unfair, because look, break it up in different ways. Okay, we're talking about the probability that an X spin measurement of a Z spin up eigenstate is going to come out up or down. Okay. What do you mean no?
Yeah, I'm there are two propositions I could have associated with your utterance there.
Let me finish my but look, but they don't on on the Everettian view that you're advocating, which I think is really interesting, as I said in the talk, for all kinds of reasons. But what you're saying about it here seems to me a little unfair. We're interested often in ordinary scientific work in discussing the probability that a z-spin measurement of an x-spin eigenstate will come out up. Okay, that's just a question that, as a matter of fact, occurs in laboratories all the time. Okay, good. All these other theories that don't discuss any indexical propositions have answers for that. Okay, on the kind of Everettian theory you're talking about, okay, you're going to say, oh, that turns out to be an indexical question. Okay, okay.
So what I'm going to say is, the question is David, where that proper name picks out a particular four-dimensional worm on a branch where, on a branch where the electron.
Question. But Isaac, that's not the question. That's not the question that I'm talking about.
Okay, look, just to make progress, give me a proposition. Just say, what's the proposition you want to assign a probability to?
The measurement will come out up.
The measurement will come out up.
Yeah.
And what does the definite description, the measurement, refer to? On my picture, there are two space-time worms.
Yeah.
That you might be meaning to refer to. So tell me, which one are you referring to with that?
No, I'm not referring to either one. I'm referring to the total process that comes out of setting up the experiment in the first place.
If you're not referring to either of them, you don't have a well-specified proposition yet.
What are you talking? Wait. And Isaac, think about Bohm's theory. Think about GRW. They can associate perfectly definite probabilities with the proposition. Yeah. The measurement will come out up without further indexing.
Yeah, no, I know. Yeah.
Okay.
Yeah.
So that's what I'm talking about.
You're criticizing the Everett interpretation. I'm talking about how this is supposed to work on this particular picture of Everett. I'm not criticizing or saying anything about those others.
No, sure. This is part of a more global criticism. I mean, I misunderstood your question. So maybe I misunderstood the question from the beginning. There isn't.
Yeah. Sorry.
I agree that if you compare what you talk about with just something that says the wave function, evolves according to Schrodinger's equation, yes, then you're assigning probabilities to propositions that don't even come up in that uncentered picture of just the whole world evolving according to the Schrodinger equation. That wasn't the point I was trying to make. The point I was trying to make is that there are questions that come up in laboratories, like what's the outcome of this spin measurement going to be, okay? Which on Everettian views like yours, and I think on all Everettian views, if you really try to make sense of them, okay, are going to have to be read as indexical, okay, in a way that they don't have to be read as indexical on theories like Bohm or GRW or something like that. That was the point.
Yeah, on my view, so the big picture point I was trying to make was more phenomena are being accounted for in this approach, not less. The reason I was making that was the proposition you just uttered. I could associate a day-say and a non-day-say proposition with it. The non-day-say one's going to get probability 1. The day-say one's going to get probability given by the Born rule.
Right.
So in that sense, the proposition that is accounted for by Bohm and all these other interpretations, that is accounted for.
I completely agree with that. It's just that on these other interpretations, the day-say question just doesn't even need to come up in the context of ordinary scientific practice.
Yeah, I agree with that. But that's why I'm saying it's a strict expansion of the range of phenomena.
I don't think there's any disagreement here.
Okay, okay, thanks.
Great. The next question I have is from David Wallace.
Thank you. A very quick comment on something Sean said before I ask a main question. I sort of think that none mad dog, tame poodle Everettians think about the mad dog Everettians roughly the way centrist Democrats think about I don't know, Alexandria Ocasio-Cortez or something. We disagree on some of the precise details, but it's great advocacy for the broader program, and it moves the Overton window-based satisfactorily. The more serious comment was, or sort of question was more to David, that touched on something Sean said. I mean, operationally, we know how we use probability in physics and science general. We know there are these things that we determine by doing measurements of frequencies, and we know we have certain inferences from sufficiently solid probability, sufficiently close to 1 or 0 that we're willing to make defeasible, pretty damn confident predictions as to what's going to happen, and we're willing to falsify theories that make probabilistic claims sufficiently close to 1 that we then fail to observe. But then as soon as you start looking at what the underlying philosophical justification of that is, even outside the Everett interpretation, of course, all hell breaks loose. It's intensely contentious what these things, probabilities are, and how these various inferences between frequencies and probabilities actually work. So David is inclined towards some situation where the probabilities are more or less reconstructions from the actual current frequencies. Other people who also non-Everettians have other takes on what the probabilities are. It's really contested. Lots of people would throw their hands up. David Lewis famously threw his hands up. It's highly contested which things count as objective probabilities and which thing counts as Ersatz. David thinks that the stat-mech probabilities are genuine probabilities are in the meaning of the act. Lewis, again, famously didn't think that. So it's all a highly contested mess. And one response might be, well, okay, it's a highly contested mess, but I have a perfectly satisfactory account of probability. I've solved all those problems to my satisfaction. And therefore the Everettian hasn't solved those problems to my satisfaction. And that's why I don't like the Everett interpretation. And that's intellectually totally reasonable. But I get the sense from David that you have something a bit stronger in mind, that you kind of think there's a particular problem for the Everettian that isn't just mirrored by the general philosophical chaos about probability, and that it would be intellectually reasonable to say, well, I have no real clue about what the right answers to these various puzzles in the philosophy of probability are. Still, the Everettian position is much worse off as regards probability. And so to David, the question is, well, what really is the justification for that? There's always a concern it's going to be just that we're just complacent. We erroneously thought the universe wasn't branching, and therefore we formed a whole bunch of presuppositions on this basis. And to Sean, the question is, you were quite keen to say that actually these things are not your grandmother's probabilities. Let's accept that in the Everett interpretation, we're doing something really different from probabilities. We have a lot of façon de parler and so forth. And I just wondered if Sean might say a little bit more about that, what the case is for saying, well, there aren't probabilities, rather than just saying there are probabilities. It turns out that we misidentified them and they were Everett mod branches all along, but that doesn't mean that all these people talking about probability and using them in physics were wrong.
So, Sean, I can start, or you can start.
Why don't I go first, because I predict that I will be briefer. I think, yes, I think that, I mean, part of my willingness, eagerness to admit or emphasize that these kinds of probabilities are different is just, doing my best to be welcoming to as many people into the broad tent of Everettianism as possible. But I do think that it's still true that there could have been a world where things were fundamentally non-deterministic. I mean, the way that I like to say it is, Bohm, GRW, and Everett, the way probability works is legitimately different in all three of those cases, right? In Bohm, it really is ignorance. There is some microstate of the world. There is some state of all the different particles, and we just don't know what it is. In GRW, it is legitimately stochastic. And in Everett, it is, everything is deterministic, and we just don't know where we are. And I think it's perfectly okay to admit that those are very different. And so, but are also similarities. So I tried to draw out the fact that, even in the GRW case, you could think of probabilities in that case, which are sort of the closest to our standard frequentist intuitions as self-locating uncertainties in the set of all possible futures of the world, right? I mean, there's possible worlds, and in all those possible worlds, wave functions collapse at different moments in the future, and we don't know which of those possible worlds we live in. And probabilities in Everett are like that in some ways and not like that in other ways. And so, you know, I think that heightening those contradictions is a good strategy going forward.
And look, I would, this is a very open-ended conversation that one can start this way. But yeah, I guess I do tend to be suspicious of the line that, oh, well, nobody understands this stuff anyway, so anything goes. I mean, I guess something that's been common to every use of probability that you know came up in scientific or ordinary life discourse prior to Everett was some claim like, if I say the probability of this experiment coming out this way tomorrow is 0.7, okay, then there's something about what things are going to be like tomorrow that I don't know right now. I don't, you know, the concept of probability might evolve in the course of philosophical investigation in such a way that we drop that, okay? All these things are defeasible. But the claim that the claim that there are the perfectly true claim that there are long-standing philosophical controversies about the meaning of probability doesn't mean that there are certain statements which were both widely agreed on prior to Everett and which Everett denies. So I don't know. I don't want to say anything more definitive than that because I don't want to pretend to have a more definitive position than that. But it doesn't seem like a completely accurate description of the situation to say, to note correctly that there are longstanding philosophical controversies about what probability means, and to infer from that that there are no statements that one can put one's finger on about probability which are denied by Everett, but which would have been widely agreed upon before Everett entered the picture. Also, just about what Sean was saying, this gets back to the short discussion that you and I were having about statistical mechanical probability a few minutes ago. I'm not sure that I see the big difference between, say, GRW probability and Bohm probability or classical statistical mechanical probability. If I was, you know, if I had no ignorance, okay, about the entire history of the world, then none of these probabilities would be relevant, okay? If I had no ignorance about the entire history of the world, all these probabilities would go away, okay? There are certain kinds of ignorance about the future, which if it went away would make GRW probabilities irrelevant. There are other kinds of ignorance about the present microstate of the world, which if they went away would make statistical mechanical probabilities irrelevant. There are slightly other kinds of ignorance about the location of the world particle, such that if it went away, the probabilities in Bohmian mechanics would become irrelevant. But I think all these probabilities are in the sense in which you're using the word epistemic, they're all epistemic. Ignorance goes away, all these probabilities go away, okay? But I don't think that should license contrasting, calling them ignorance probabilities with there being real, genuine chances out there in the world. And I'm not sure. Now, this is more specific. This is what David was earlier alluding to as a very particular view about probabilities within the debate. Okay. Yeah, for my money, the chances we run into in statistical mechanics are just as much fundamental physical chances as the chances we run into in GRW or the chances we run into in Bohm. All ignorance goes away, all those chances go away. Okay. So I guess that's it, but that's to be separated. Well, I've already said this about what David said. I think there are things that we don't know, and I think there's a lot that we thought we knew, but you know, before people started trying to insist that what we were encountering in Everett were probabilities too.
Oh, okay, but before but before the 20th century, it was pretty much a commonplace in discussions of probability, you know, between Laplace and various frequentists that of course the underlying physics was deterministic. So that was a kind of common assumption that they're doing. Now, the point is, it was an assumption that wasn't load bearing. It wasn't actually doing any work in the scientific activity of checking and tasting the probabilities. It was just a shared philosophical take on what probability is based on a false belief about the world. So the analog would be something like that, the assumption that probability always relates to some concrete third-person fact you don't know about the future. Yes, that was common to all these approaches because it was based on a shared false belief, but it wasn't load-bearing. So the success of the scientific use of probability doesn't give you evidence for it.
Yeah, and look, maybe all I can do is confess that it's a very deep part of the intuition about what one is talking about when one is talking about chances. Yeah. For me. And by the way,
it's never been nice to intuitions.
I mean, I have other objections that you've heard in the past, although I had wanted to do the first half of my talk about that, but as I said, it just got to be too long. I have other worries about the decision theoretic strategy, but my understanding about the decision theoretic strategy, at least in its fission version, was that it didn't have a dog in this fight, that it really was going to say, we're not talking about chances here. There are no chances in the world. What we have is a bunch of theorems about what your preferences are going to be in this perfectly deterministic world, which will explain how you're going to bet, okay? And there is a sort of as-if theorem, okay? But in some sense, the decision theoretic strategy doesn't have a dog in this fight and doesn't need to say, well, we're giving a new interpretation of probability. There's been much confusion about this, so on and so forth. It seems to me, I mean, I'm curious to hear whether you think this is right. It seems to me that one could pursue a decision theoretic strategy without ever getting into this fight at all.
I'd love to come back, but I kind of think I've eaten enough time anyway, so then another time.
Right, okay, great.
If it's all right, we
can
can go to the
say
next.
something myself to follow up on this very quickly. To go to David's point about, you know, there's a sense in which the probabilities that we would associate with Bohmian mechanics or classical statistical mechanics are of a similar sort to what we get in GRW theory. They're ignorance about something, either the current microstate of the world or the future state of the world. Sure, but they're also there's a big difference between them. I mean, the current microstate of the world is a different kind of thing than the whole future.
Yeah, one of them is dynamical and the other isn't. That's for sure.
Yeah, I mean, one of them is a statement about the laws rather than the state. And I think that that's an important different kind of probability, not just a different kind of statement.
No, but I don't look, but God forbid, I don't want to start acting like a philosopher here. It's true, and what everybody will readily agree on is one of them is dynamical and the other isn't. Okay, the GRW one is dynamical, the other isn't. I think that on a proper philosophical conception of what a fundamental law of nature is, the chances in classical statistical mechanics and Bohmian mechanics are no less fundamental physical laws than F equals ma is. But this is what I meant by, I don't want to, this is maybe going to sound like splitting hairs or something like that, and I don't want to go that way. Yes, surely there's a difference one can put one's finger on. The GRW laws, the GRW chances are dynamical. The statistical mechanical chances and the Bohmian chances are non-dynamical. I guess I would say, and this is the only time I'll act like a philosopher, if you have the intuition that that points to a deep metaphysical difference, I would be willing to have a debate with you about that.
Okay, I'm not going to, let's not plumb the depths of the difference. There's a difference and there's similarities.
There's a difference for sure.
Right, and so the reason why I want to emphasize this is because, I tried to say the same thing for the self-locating certainties, uncertainties in Everett. I mean, namely that there is a similarity between what you face in that case and what you face when you just don't know what kind of world you live in. And the similarity that I tried to put forward is that in either case, you need to have a set of credences to get through the day. But the difference, which maybe I glossed over too quickly, so I want to sort of, testimony against interest, is that, and I think this is what, David, you're getting at, is that unlike just putting some probability distribution on the initial conditions in stat mech or in Bohm, in Everett, you're demanded to reassert credences every time the wave function of the universe branches. And that is something very different, right? That is not just putting initial conditions once and for all, or a measure on initial conditions once and for all. So it is a different kind of metaphysical move. And so I agree that it is a different kind of probability in that sense.
That's, Isaac has a different strategy here. Isaac thinks, and this is something worth talking about. There are two metaphysical attitudes you could have towards these eyes in the context of something like Everett, or even in the context of the Kirk case, conceived classically, okay? One of them is that every time you split, new eyes are being created, okay, that weren't there before. The other is they were all there, they were all there all along. It's just that there were periods when they all overlapped, okay? I have trouble understanding both of those, okay? If they all overlap, then you've got this weird situation where the situation of the world now doesn't fully supervene on its current physical situation. You need to know how many branchings are going to occur in the future in order to know how many eyes there are right now, okay? And you interpret yourself as having uncertainty about which one you're on. On the other hand, if new eyes are getting created every time, then you're in the situation that you were just alluding to, okay, about new credences having to be formed all the time. So this is among the issues I was referring to, I guess, in the last sentence of my talk. Well, if you were going to go this way, there'd be a lot to figure out. I recommend, again, Isaac's paper about this, but he has a particular take on it, which certain parts of which are confusing for me.
All right, so we have about 10 minutes left. I want to be really mindful of time. Lev raised a finger. Lev, if you have a quick question or comment, please go forward.
Just, I didn't pursue before, but the whole point of self-location uncertainty is to say that when in Everett you ask what will be the outcome of the spin measurement, there is no answer to this question. And he was trying to find it. Everett says there is no answer to this question. There is only answer to the question when you make special arrangement. There are two different observers with, which are different in different branches, and they don't know which one. There is no answer to the question, what is the probability of the outcome of the spin measurement? Because you know, for certainty, there will be both outcomes. And all these indexical things will not help. But I should continue.
All right, the next person I have is Wayne.
We have 10 minutes. Okay, there's no way that this is only the last 10 minutes, but because I think I'm re-raising issues, David, that you and I, with the discussions we had back in 2007. But I guess, okay, let me just stress things I totally agree with you on, David. I think you're right that I think you're absolutely right that on the decision theoretic approach, there's absolutely no need to make sense of talk about probability of this outcome or that outcome taking place. On the other hand, I don't think it really matters whether you take a decision theoretic approach or something more like the one that Lev and Sean do when, after the experiment, you do have self-locating uncertainties. Because as long as you've got some diachronic coherence condition, you can ask what before, on the decision theoretic account, you can ask what credences you would recommend to your successors after the experiment, and if they're going to base their subsequent decisions on those credences, then everything meshes nicely. I also agree that there is a worry about theory confirmation and the role that empirical frequencies make. Does it make any sense to say we're confirming the Born rule on this kind of thing? But as you know, that's exactly the question that Hilary Greaves and I addressed in our paper back in the day. And it stems from the fact that, on either account, if on a decision theoretic account or one that bases itself on self-located uncertainty, okay, you can talk about what you would do if you know the quantum state. But of course, you can also be uncertain about what the quantum state is and have credences about that. And you can ask, well, what should your updating route? Suppose you've got some preparation procedure and you're uncertain about what quantum state that preparation procedure produces. You can do the experiment over and over again and update on your credences on the outcomes, and we argued that you would do the same thing that you would if you were thinking in terms of chances rather than Born rule weights. Now, one thing that's really important is that what you think you're estimating there is an objective fact about the world. What the quantum state is, or we imagined different kinds of, maybe non-quantum theories with different kinds of branch weights, but you are empirically estimating an objective fact about the world that you are, which then informs what your self-locating credences would be. And I think Sean would agree that, we can test hypotheses about what sort of quantum state you find yourself in, given a certain preparation procedure. We can do statistical analysis and test those hypotheses in, completely in the ordinary way, and then those should inform, your credence in those hypotheses should inform what you think your self-locating credences should be. So, I mean, I think that that's one thing that was missing in your discussion. And something that Sean said was, you have to take very seriously that these branch weights are physical, actual physical differences. And also frequencies can be evidence about what they are.
So I'm trying to remember, because as you say, it was a long time ago.
Yeah.
I'm trying to remember the details of your and Hilary's paper.
Yeah.
And I'm not gonna get them right off the top of my head.
I would
But,
have to look up the details myself.
I'm just wondering how I mean, here's what I remember broadly thinking about confirmation in the decision theoretic strategy, okay? That you were supposed to end up believing, you were supposed to end up giving high credence to those theories, as it were, that you would have bet on, okay? That is, we have this, in the decision theoretic approach, we have this idea, we're going to tell you, given your preferences for non-branching futures, given your preference orderings among non-branching futures, we're going to derive what your preference ordering is among branching.
Absolutely not.
Okay.
That's exact opposite. Yeah. So
the exact opposite of your strategy in that paper.
Of our strategy,
decision theoretic. Oh, okay. Yeah. So I'm misremembering. So go ahead.
Exact opposite. Yeah. So the idea was that okay, imagine that you think that you're in a branching type situation. Like someone does an experiment and various outcomes are going to occur on various branches, and you have preferences between what Barry Lower calls brambles, different distributions of outcomes. All right, yeah. And then basically. We put conditions on your preferences between brambles that has the effect that your preferences between brambles goes as some kind of weighted average of utilities across outcomes. And then further conditions over where you're acting as if you think.
Wait, that's an assumption? Isn't that what we
No, that's a conclusion.
Oh, good.
Yeah, we put conditions on your preference between brambles that have that as a result.
Right.
Basically, it's and then further conditions that under which you're acting as if you think there's objective branch weights associated with these various branches, and you're that you can have credences about. I mean, let's go to your Kirk example, because this sort of gives a flavor of what you get at the end of the day. So. Let's say Kirk doesn't know, he's going into a transporter and he knows it's going to produce a certain number of green shirt Kirks and a certain number of red shirt Kirks. He doesn't know what those numbers are, but he can have credences and various hypotheses about these.
Right.
And so you do your thing, you go into the, if I'm recalling correctly, your example was you go into the transporter. You come out, you look at your shirt, but not at the other guy's shirts. You go back into the transporter, you do again.
No, you do look at the other guy's shirts too.
Okay. Then that's not analogous to the Everettian case, because you don't.
True.
So here is a amendment to your.
Okay.
So you don't look at the other guy's shirts, but you do it again and again and again and again, and you keep a record of how many times you see a green shirt and how many times you see a red shirt.
Good.
Now, and I claim that you can update your credences about what those numbers are on that. And if you do this like 10,000 times, and 2/3 of the time you see a red shirt and 1/3 of the time you see a green shirt, on a reasonable way of updating your credence should become fairly well concentrated on it being a ratio of 2 to 1. And you'd say, okay, well, all right, there's going to be all these other guys who saw, and let's say it really is 2 to 1, two red shirts and 1 green shirt. And you say, well, I know for certain that there's going to be at least one, there's going to be, one guy who saw a unbroken string of green shirts, right? Right. But you also know that whatever the actual frequencies are, like if it is 2 to 1, then there are more people who have their credences concentrated on I hypothesis than there are people, right? And so similarly in the Everettian case, you do this thing.
No, but wait, stick with the Kirk case. Am I supposed to draw a conclusion from that?
I have to interrupt for just a moment. It is 4 o'clock. So
Yeah.
we're out of time. I want
told
to be
you it was going to take more than 10 minutes.
So sorry.
Okay, all right. No, no, that is so. Okay, my claim is that that is the proper way to update your credences in a situation like that, and you should.
But that's
and
exactly
the fact that with certainty there will be some people that we're wrong is not an objection to the claim that that's the right way to update your credences. That's what I'm claiming.
Okay. And of course, but this is what would take longer. One wants an argument. But good. I'll have to look back at it. I apologize. I just don't remember it off the top of my head.
I don't either.
But good, Jacob. Thank you. I mean, do you want to wrap things up somehow?
I was just going to wrap up by saying thanks to our speakers. Thanks for everybody for all of your questions. I'm so sorry we didn't have a chance to get to everyone's questions. But you know, I hope we'll see many of you again at the next workshop in the series. Please stay tuned for an announcement very soon. And be safe, everybody, wherever you are.
Thank you, Jacob.
Thank you, Jacob.
Thank you.
Thank you, Jacob, very much.
Thank you. Thank you.
And stay tuned. The recordings will be posted online very soon.
Thank you, Jacob.
Thank you very much.